Decision making under risk using Microsoft Excel. In one of my YouTube content, I've been able to show the theoretical explanation of decision analysis, especially the computation of decision making under risk. In this video, I would like to show you the same thing using the Microsoft Excel. How can you compute for the decision making under risk using the Microsoft Excel? This is an example. We have the decision payoff table and we are interested in the expected payoff value. You have the decision alternative 1 small, 2 medium, 3 large, and we have the probability estimate attached to each of the state of nature. The state of nature is occupy the columns here, while the decision alternatives occupy the row. The small, the medium, and the large is the decision alternatives. So how do we compute the expected monetary value? So the first thing first, we need to verify that the probability value is equal to 1, because we are expected that the sum of probability has to be 1. Now, we need to know the expected monetary value for each of the decision alternative. So for the first one, we're going to use the sum product. We're going to highlight for the small array and for the probability value, which will be locked because we're going to be referencing the probability value. So we're going to do the same for others, and the addition of this the maximum, the highest of this expected monetary value under each decision alternative will be considered. So in that case, the highest falls under small, and that is why by the expected monetary value we are going to consider the decision alternative small. Let's look at the expected value of perfect information. To compute the expected value of perfect information, we need to do something interesting. And that thing is, we need to look at the maximum value under each state of nature. So for the first one, out of 10,000, 8,007, the highest is 10. For the second column, 20,000. For the third column, 9,000. So we are going to use the sum product function as well to multiply the probability value by these maximum values obtained from the state of nature. And by the time you take the subtraction of the expected monetary with perfect information, you take it away from the expected monetary value you obtain, it will give you the expected value of perfect information. And that is why we have the EM slash PI minus the EMV. So this is expected monetary, the expected monetary without the perfect information. When you subtract it from when you subtract the expected monetary value from it, it gives you the expected value of perfect information, which is what we have as 800. More so, if I want to compute the expected opportunity loss, which is the EOL, I need to determine what happens by looking at the highest under each state of nature. So I need to compute the regret table first. So the difference between the highest value under each column minus each of the entries in that column, and that is why we have this. So you can see the 10,000 was referenced all through. The same thing applicable to the second column under the regret table. The highest is 20,000 minus each of other entries, and you have this. So we do the same thing for this now. Having done that, we need to compute the the multiplication of the probability value by each of the decision alternative results we obtain in the regret table, and that's what gave birth to this. Let's do that again by ourselves. Equals sum product. We are multiplying this by the probability value, which I'm going to lock using the F4, and I'll press Ctrl Enter. So it's going to do for others since I've highlighted on everything. And by the concept of expected opportunity loss, we are going to pick the minimum out of the 800, 4006 and 78, and that is why we consider the small as the decision using the expected opportunity loss. So we are able to see that both the expected monetary value and the expected opportunity loss was able to recommend us going for small, not medium, not large. So this is how you can find your way around decision making under risk using the two criteria, expected monetary value and expected opportunity loss. Once again, we have also been able to look at decision making under uncertainty using the 5 criteria: the maximax, the maximin, the minimax, the always, and the Laplace, using some theoretical explanation. You can also do this using your Microsoft Excel. We have this table, and from this table now you can see the state of nature x1, x2 up to x4. So for us to get the maximax, that is the maximum of the maximum value, you use the max function, and you'll be able to get that by the maximax criterion. Where do you have your 14? You have it under D1, so you should consider D1. The same thing for the maximin, that is the maximum of the minimum. So you are going to compute for the minimum value first, and you choose the maximum of that minimum value. So let me try to freeze this so that we can see that better. Let me freeze. Okay, so you can see now that we are able to compute the maximum of the minimum value. Also, we have the minimax, which requires you to compute the regret table, and from the regret table, as you can see here, we're able to compute the regret table by looking for the highest under each column, and we subtract it from each entries. So the resulting table is what we call the regret table, and from that we pick up the maximum under each decision alternatives, and finally we're going to look at what is the minimum of this maximum value, and that's what gives birth to what we have under the minimax criteria. More so for the always, we consider using the weighted average, the WAP, weighted average payoff formula. And from the weighted average payoff formula, we are able to get this. So the computation was done here, the WAP was done here. Let me show you. The WAP was done here. We consider an alpha to be 0.6 and 1 minus alpha will be 0.4 since the sum has to be 1. We do the computation for each of these till we get to the final one. The same thing was done to the Laplace, which is the criterion of equal probability. Using the formula 1 over n, which is the number of states of nature, multiplied by the sum of the values, we get the expected payoff for each, and finally we're able to consider D4 since the formula was able to pick up the maximum value